Okay, Assalamualaikum and good morning. So today we will learn about vector fields. This vector, we have arrow here, vector. It used to represent, we know that for vector we can represent speed, direction of speed, direction of force, flux, and also magnetic field. That quantity they have direction, so we can present the direction by using arrow. Arrow is a vector field. So it represented by Cartesian. We know that this one 3D coordinate. So Cartesian, cylindrical, and spherical. So for this one is vector field for Cartesian x, y, z. This one is vector field for cylindrical r, phi, and z. This is example of vector field. What kind of field is depend, maybe speed, maybe force, flux, or magnetic field. Okay, this is arrow direction. We want this arrow go into one point center, and this one is the arrow look like converge. This arrow look like it curve. Okay, so we call curl. This is converge or diverge. So next is, okay, this is the example sketching of vector fields. So let's say we have function x, y, and z, which is for Cartesian, is equal to minus direction y direction of x plus 2x direction of y. Let's take x equal to 1, y equal to 1, so at this point. And then we substitute x equal to 1 here, will become minus 2x. Sorry, 1. 1. So 1 is 0.11. So just replace 1 here and 1 here, it will become minus x plus y2. Means that minus x coordinate minus 1. This is 0.1. So minus 1 means that go to the left one digit or one segment. This one is plus 2. Plus 2 means that go to positive y2. 1, 2. Okay, here 3. This is our vector here. So vector will be here. Yeah. Left minus 1 and plus 2. Next is, let's say we put 2 and 2. Okay, 0.2 and 2 is here. This is 0.2 and 2. So just substitute value here. Substitute 2 here and also 2 here. It will become minus 2x plus 4y. So from this point, 2x means that negative 1, 2 at this point, and then plus 4. 1, 2, 3, 1, 2, 3, 4. 4 is here. Means that the direction of vector field is like this. Next example, if we put minus 1 and minus 1, just substitute minus 1 here, minus 1 here, it will become x is x minus 2y. So it means that at minus 1 point, if there is point, the vector field will be plus 1 and minus 2. Okay, plus 1, minus 2 will be here. This is a vector field. I think the rest in this slide, you can have a look. So any question to sketching a vector field just by substituting the value of x into the equation and then we plot it. Okay, next is example number 2. This one is cylinder. We know that for the cylinder, the coordinate for cylinder will be x, y, z. Okay, cylinder. Okay, let's say this point. Point A. So this one is R, Z, Y, X. Angle is here. Phi, Z is this value Z. So the given equation is equal to, okay, R only. Okay, this just direction of R. We know R is here from Z axis to point A. From Z axis to point A. And also for the formula, we know that R is here. R here, formula R equal to square root X plus Y. This is value for R. So let's take 1 point 1 here, this point. 1 and 1. 1 X, Y equal to 1, 1. So what is the value of, okay, 1, 1 here, value of R will be equal to, substitute 1 here and 1 here, it will be equal to square root 2. Square root 2. So at which direction? So we know that the direction is from Z axis, go out. So in this case, we have X axis here, this is Y axis. So Z axis go out from this one. Like this one. X, Y, Z. Z come out from this, from the board. So means that the direction of R will be like this, from this point. Next is let's put the point x, y equal to let's say 2 and 2. So just substitute 2 here and 2 here. So will become R will be equal to 4 plus 4, means that's 8, square root of 8. So at 2 and 2 is here. So this is R. Example is minus 3 and 3. X, Y, R equal to square root X plus Y. Let's say we put minus 3 and 3 here. So R will be equal to 9 plus 9 square root 18. Okay, this one. The direction is out of from Z axis. This is Z axis. So out of from Z axis. This is Z axis. This one is Z axis. So we look from here. Our eye is here. So it means that it come out from Z axis. Z axis. In our case, Z axis is go out from the board. So the arrow will be like this. For 3 minus 3 and 3, the arrow will be like this with the magnitude of 18. Okay, this one is magnitude of 2. This one is magnitude of 4. So let's say we put x equal to 0 and y equal to -1 here. X equal to 0 and y equal to -1. R will be equal to 0 plus 1, so 1. Okay, this is the magnitude for the direction come out. Direction should be come out from Z axis. So this is the magnitude is 1. Okay, any question? How to sketch a vector field? So we just replace the value of X and Y. So next is scalar field. Okay, scalar field, it represents the distribution of a scalar quantity in a space. It can be used to represent the value of, this is just number, value of mass, anything that non direction, we call it scalar fields. So height, temperature, size, anything that no need direction. So it can represent in terms of value, numbers or value. In this case, we have a scale value here, 50, 40, 10. So it means that maybe this one is 50, this one is 40, and 20, 10. Okay, it's the value in a space. It's our space, the value in the space. The value can be a numbers, number maybe height. For example, let's say is we have a mountain. So mountain will be like this. So we can represent. So when we look from top of the mountain, we will see like this. Okay, this is the highest top one. Maybe the highest one, let's say 100 meter. Now is 50 meter, 10 meter. Okay, 50 meter, 10 meter. So we can represent in scala like this. 10, 100, 70, 20, 50, 70, 70, 70, 70, 50, 50, 50, 50, 10, 10, 10, 10. Okay, this is when we look, we call contour. I believe you already learned in your geography about this scalar field. So scalar field represented by Cartesian, cylindrical, and also spherical. All right, any problem, any question regarding vector field and scalar field? Vector field represent direction, scalar field represent the value of number. Now we go to vector calculus. It's a differentiation of vector fields. So we have 3 types of calculus that we will cover: gradient, divergent, and curl. Okay, this one is del or nabla, symbol for nabla. Nabla, okay. Okay, del operator. So this is del operator. Del operator denoted by as a nabla. Nabla, triangle, flat at the top. It's a vector operator in vector calculus. It is to perform various operations on vector fields, such as finding the gradient, divergence, and curls. Okay, the del operator is defined by d over dx, I plus d over dy, j plus d over dz, k. This one is direction of the axis. In this case, we have I, j, k axis. If we have x, y, z, you can replace I, j, k with x, y, z axis. When this del operate on a scalar function, del operate on f, the output is a gradient. when we use del, this del operate to the f, a scalar, the output is gradient. Okay, number two, when del operate on a vector function via dot, del dot vector. Okay, let's say A. So this will become divergent. So when del, we use del operate cross A, it will become curl. This is we call gradient, divergent, and curl. Del times scalar, this is scalar, so it will become gradient. The output of gradient is vector, unit vector. So we have direction. The output of divergent unit is scalar. For divergent, del dot scalar. So sorry, del dot vector. Del dot vector. So unit, the output will be scalar. For curl, del cross vector. So the output will be vector. Okay, we will go one by one after this. Okay, what is del? Okay, before we go to del, just review on differential operator. We know that we have let's say we are equal to let's say x over 2. So differential operator means that f prime x equal to df over dx equal to 2x. Okay, just using the differential equation or this function, it will become 2x. This is we call differential operator. Means that the variable is we differentiate it with respect to x. Or in terms of graph, we can draw like this. X here, this is fx. So x squared will be equal to here, x squared. So df over dx means that we check the slope here. df, this one is x, dx, this one is df. So df here, dx here, df here, dx here. So what we get is the slope. Slope of the graph, slope of the curve. Okay, this we call differential operator. This case for just a single, just one we call one function, just function of x. Let's say we have another function of y. Let's say we have function of y, x. Let's say we have another function of y. So there will be we have two axes. So when two axes, there will be we call to do this we need to. Okay, this one is just a curve. Rate we call rate of change. Rate of change at this point or curve. For 2D, okay, this one is 1D. This one is 2D. Let's say we have two graphs. So then it will become maybe like you have two function of x and also function of y. So means that there are two axes. For example, we have a function of y like this. This is function of y. This one is function of x. Function of x. So it will end up as space. This one is space. Okay, this is due to two functions. Compared to just single function. Is it just a single line? This one is look like a space. So this one, the rate of change is we call the slope, and this one we call a surface. We have x, y is equal to let's say x, y power of 3 plus x power of 2. So to differentiate it, we have to use, we call partial derivative. Partial derivative. Derivative. This one. Okay. This is called partial derivative. So we have, means that in this case we have two axes. So we have to do individually. So partial derivative for x and partial derivative for y. So first for x, df over dx will be equal to, we take this one for x only. Okay. D over d, the x y power of 3 plus x power of 2. It will be equal to, boleh buat tak? So x power of 3, x will become, so y become a constant. We differentiate this equation with respect to, sorry, we differentiate that equation with respect to x, okay, dx, and the y will become a constant. So it means that in this case, y is constant. So just we differentiate with respect to x only. So this will become, x will become 1. Y is constant, so they will become 1 y power of 3 plus, the second one is 2, okay, it's 3, yeah? 3 or 2, okay, 2. So 2x, it will become 2x. Number 2, we differentiate, we do partial derivative for dy. So dy x y power of 3 plus x power of 2. So it will become, this one is, so we done, okay, y. So differentiate this equation with respect to y only, to y, and then x will become constant. So x is constant. So then if we differentiate y3, it will become 3 y2x plus, so this one is constant, so this one is 0. Is there any problem to do partial derivative? If no, I will continue. Okay. Okay. So actually this one is we do partial derivative individually, separately. Then we can combine both solution. So our solution will become y, combine both, huh? Wait, fxy y power of 3 plus 2x. Okay, this one is we differentiate, we do partial derivative with respect to x. So this one we call x axis plus This one, we do partial derivative with respect to y. So we can call y as this 3y x. This one is y as this. Okay, this is we call the gradient. Gradient of f. So we can see that this one is x, this one is y. So means that the output will be a vector, unit vector. We have x as this, and also we have y as the direction of x and direction of y. So output will be unit vector for gradient. This is called gradient. The gradient is the combination of partial derivative. This one. The gradient is vector operation of which operate on the scalar function to produce a vector. So the input is scalar vector. Okay, the gradient is we do operation nabla to scalar. F is in scalar, so the output will be vector. Show we have magnitude is the maximum rate of change of the function, and also direction to the maximum rate of change. Only for Cartesian, we have x, y, and z. So we do partial derivative with respect to x, and then we let y and z is constant, and then we plus partial derivative with respect to y, and z and x is constant, and also partial derivative with respect to z with the condition of y and x is constant. Then we add all together, it will become a gradient of our function. For example, unit scalar. So we have the given scalar. Let's say this is our scalar. The scalar show as previous one. Okay, this one. This is scalar. For example, this scalar show the height of mountain. We have number here. Let's say, for example, 10, 10, 10, 10, 10, 10, 10, 10, 10. Twenty, 20, 20. Show the height of mountain. Uh, 50. So if we plot for 3D, let's say this one. Y as this, x as this. This is our height. This one is 50, 50. At the center. For example, 50 meter. 20, okay, the surrounding is 20. Okay, draw in 3D. Draw in 3D. Okay, x axis and y axis. 20, 20, 20, 20. This one is 10, 10, 10, 10, 10. This also scalar. Okay, when we apply del operator on the scalar, so the output will be gradient. Scalar, and the output is vector. Output is unit vector, input is scalar. We do del operator on the scalar function. One, we do del to this. Let's say this is function, scalar function. We do del here, so output will be vector. What is our del? That's the gradient. So we have a graph here. You know that there will be okay, from this one. Slope here. Slope, the direction show the, okay. Direction of arrow show the towards the magnitude is the maximum rate of change of the function on the point of gradient, which point in the direction of the maximum rate. Okay, this one is maximum rate. Maximum rate is 50, so it will point to 50. So if we look from top as this, x, y, okay, x, y is x, y, sorry, x and y. We look from here. Our eye is here. What we can see is x, y. What we can see is the direction of vector. Okay, this one is top of the mountain. Direction of the mountain. Direction of the vector is show to the maximum peak. So direction of the maximum rate of change. This is unit vector. Unit vector. The output will be unit vector. So this is scalar. We apply del here to this scalar. The output will be unit vector. This is called the gradient of the function. Any question regarding the gradient? No question. Okay, now we go to the next one is divergent. Divergent, when del operator operate on vector function via dot product. Okay, this one. Our del with dot vector. The output will be divergence and the scalar in it. Okay, operator dot vector. Okay, they will become divergent. Our divergent is scalar in it. Scalar in it means that there's no direction. Divergent quantify the magnitude only. Yeah, no direction, just a scalar of the amount of vector field which flow out into a specific region. In other words, divergent calculate the amount of source or given field of a given field. Divergent is a scalar function of a vector field. So far, okay, that? This vector, okay, this kind of vector is not gradient. It can represent speed or force, same vector. Okay, our vector, it can represent speed, force, flux, or magnetic field, or anything. So when we do del operator, we dot our vector. Let's say we have vector here. So when we do del here, del dot this vector, the output will be scalar. For example, okay, we know that we just plus, so there will be, the output will be unit scalar. The numbers, output will be numbers. Our number is greater than 0. This kind of direction we call divergence. A greater than 0. If del operator to the A unit vector greater than 0. positive number. Okay, this we call divergent. So our graph will be diverge. At this point, diverge. Like this graph. If delta A negative number, so it will convergent. 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 Okay. This one convergent. Or sometimes we call sink. Like same as our sink key, when the water flow to the point. This one sometimes we can call source, S-O-U-R-C-E, source. For example, water source, there will be out, magnetic field out. For example, magnet, so plus, there will be magnetic field go out. This one is sink, negative charge. This one is positive charge. Okay, the third one is curl. The calculation of curls quantify the amount of direction of vector field. The vector function via cross product. We do cross. The output is curl. We apply vector cross product, vector, output will be vector. As I mentioned last week about right hand rule, cross product. When we have, let's say we have A, B, A cross B, vector A cross vector B, there will be vector C. So vector C will be, we can use right hand rule. A times B, so direction like this, and C will be go into X, Y, so that use right hand rule, X, Y, Z will be go up. Okay, C will go into C, into the board. So vector cross vector, there will be another vector, C. So for this one, X cross Y will come out as another vector Z. So this is we call curl. Use the right hand rule for this one, curl. This is curl, and our direction will be go into. This curl is counterclockwise. Use your right hand rule. Counterclockwise. Fingers show the direction of this arrow, your fingers, and thumb will be go up. And if you use your right hand rule to this one, your fingers show direction of arrow, so the thumb will be go into. Okay, go into. This one go out. This one we call positive curl. This one is negative curl. Positive curl. For curl A, so we have to use metric X, Y, and Z. So metric number is metric. So for example, calculate the gradient of scalar field here. So the given is scalar, unit scalar, and the output will be vector. So first we do partial derivative. Okay, this one we do partial derivative with respect to x. We have three, x, y, and z. So we do this one with respect to x. X dv over dx plus y dv over dy plus z dv over dz. So first dv over dx, x dv over dx will be equal to, okay, take this one, we do a partial derivative with respect to x. So now this one will become 2x, y is constant, then 2x, y. This one is, when we do partial derivative for this, will become yz only, plus 1, okay, yz. Next, we do y dy over dv over dy with respect to y. When we do with respect to y, this will become, y will become 1 at power of 2. At power of 2, this one is xz. So now we do partial derivative with respect to z dv over dz. So this one, there's no z, so will become 0. For this one, z will become 1, so plus xy. And finally, we just add all this one plus this one plus this one. So this one plus this one plus this one. So we can see that this is x direction, y direction, and z direction. So this will become vector field. Example number 2, we do scalar. Calculate the gradient of the scalar field. So we just using cylindrical. One by one. This one, first we do partial derivative with respect to r. Then we will get this value. And then we do partial derivative with respect to phi, get this value, this value, p, and then we do partial derivative with respect to z, we'll get this value. Gradient, divergent, we just do dot product, dot here, so the final value is here. The output will be scalar. Okay, you can see that there's no direction, there's no x, y, z, there's no direction, so the unit is scalar only. Okay, the input is, for the input we have x, y, z, we have direction, input is vector, output is scalar. The one is divergent. I think you can do by yourself. Now it's already 12 p.m. Okay, I think that's all. Any question? So hopefully you can understand what is del operator, what is nabla. So in today's lecture, we discuss about del operator. It can operate on scalar field, vector, and also vector. There are 3 types of del operator. Operate on scalar function, it will become a gradient. If you dot scalar function, dot vector, it will become a divergent. If cross vector, it will become curl. Okay, that's all. Thank you very much.